Okay, once more, we have the sphere centered at 0, 0, 1, the first quadrant of the xy plane, trying to find the moment of inertia about the z-axis. Given this density function, we can do that in x, y, z coordinates, and we can do that now in a different coordinate system consisting of r, theta, z coordinates, the system that we'll call cylindrical coordinates. And we want to just look at this region now strictly in terms of the cylindrical coordinates without reference to our x, y, z coordinates, and try to verify that we really do have these limits on our integral. Now I've sketched an XYZ plane. This is from a perspective down close to the XY axis out in this direction somewhere. And I've marked off unit distances on the X, Y, and Z axis. I've marked off 2 unit distances here because the center of the sphere is 1 unit above the XY plane, and the sphere has radius 1. So what we want to do now is we want to think of this in terms of r, theta, z coordinates. So first of all, we know that our sphere lies above the unit circle down here in the xy plane. So I'm going to draw the boundary of this circle as it would appear from this perspective, and consider the partition. How do we partition the regions of the plane? We partition them by delta thetas and by delta r's, giving us typical partitions much like the one you probably can't quite see here. Our sample point lies within this partition, and what we're really interested in is how high we've got to go before we hit the sphere if we move directly above our sample point, and how high we have to go before we hit it again, so that we know which region of the sphere lies within the slice of volume corresponding to this interval. So if our sample point is here, let's say, okay, so we got a sample point and we've got the set of points lying above this sample point. Now we haven't drawn the sphere, and we're not going to attempt to draw the sphere. All I'm going to do here is draw the portion of the sphere that comes out in the direction of our sample point. So if this line goes from the origin through our sample point, and I've extended it a little further so we can see it, then we have some r, the distance from the origin to the sample point. We have a theta, the angle from the x-axis around to this line. Where's our sphere? We're interested in the point that lies above our sample point, so we're going to be interested, or we're going to be able to confine ourselves to the set of points that lie above this line and on the sphere. So we simply sketch the portion of the sphere that's sliced by the plane that lies directly above this line. Now that portion is going to come out to r equals 1. Right here is the r equals 1 point. So at every point above here, that is part of the r equals 1 plane, or the cylinder, okay? And I guess it's as good a time as any to digress to the fact that anywhere along this circle, the set of points that lie above and below this circle of radius 1 in the xy plane form a cylinder, form a right circular cylinder based on this region of the xy plane. And this is very much related to the fact that we call this a cylindrical coordinate system. Okay, now this particular line lies at the appropriate angle theta. The sphere centered at this point, having radius 1, comes out to this line And if we draw a segment parallel to the line we've drawn in the XY plane, we see that this point is going to lie on our sphere. It's going to be 1 unit from the z-axis and 1 unit from the point 0, 0, 1, which is the center of our sphere. So it's on the sphere. Its length is 1 because its length coincides with the distance from here to here. Everything here is a right triangle. From this point to this point to this point to the origin and back forms a rectangle. Actually, in fact, in this case, a square with sides of 1. Now, the surface of our sphere, as it intersects the plane that we're beginning to form, lying above this line, will go from here to here to here. And it's going to be a circle, obviously. So we have a circle that starts out in this direction, starts out parallel to this line, and is going to end up coming in parallel to this line, but then curves down to this point and back. So let me grab a different color. Not sure how well this will contrast. I'm not sure how good this is going to look, but we start out in this direction. We come down here to where we're tangent to this line, and then we come back to the origin, and that might look something like this. And right here is a slice of our sphere. With the important characteristic that our sample point, which is hidden in the mess that we see here, that the vertical line from our sample point will intersect this half circle and will lie inside the sphere between the 2 points of intersection. So that we have our intersection points of the vertical line above our sample point with the sphere. And those points lie here. That one's easy to see. And there's another one down here because of the perspective and the shading and probably a bad choice of how big to make the picture. We have another intersection point down here. If I look at this plane parallel to this line and the intersection of the sphere with that plane from a right angle, from a direction that makes a right angle with that vertical plane, I'm going to simply see a half circle here lying above the sample point. So what I'm going to see is my z-axis is going to be here. Let's just imagine rotating this line around, or rotating our perspective around to where we're looking at it in this direction. So along this direction, we're measuring r. Okay, this line here corresponds to this line here, and the distance from the origin, which corresponds in both pictures to a given point out here, is just going to be our coordinate, our distance from the origin. Our half circle is going to go from, it's going to be centered at z equals 1, and let's say r equals 1 is out here. And this is not going to correspond too well with what I've pictured, but our half circle is going to look something like this. It's a little bit distorted, but it's at least good enough to serve as a reference. Okay, so what's our r coordinate at our sample point? That's r sub I star. And our vertical line comes up like this. If we draw a segment from the center of the sphere